When nuclear fuel is sent from power stations to Sellafield in Cumbria for reprocessing, a simple procedure is used which has now been carried out safely more than 14,000 times. The fuel rods are first cooled for at least 90 days at the power station in dry storage or by immersing them in ponds. When they're taken out of storage, the heat coming from each rod has dwindled to about 25 watts, roughly equivalent to the warmth from a small electric light bulb. About 200 rods at a time are loaded underwater into an open-topped steel skip, which is then placed inside a special container called a flask for transport to Sellafield by road and rail. The flasks are very robust. They weigh about 50 tons and have walls 35 centimeters thick. 16 bolts, each able to take a load of 150 tons without breaking, secure the lid. Their bodies are forged out of single ingots of steel, heated to 1200 degrees centigrade, and then literally squeezed into shape. They're compressed in pairs, which are then lanced apart. Checks on their mechanical properties are made, and they're inspected all over ultrasonically. The flask lid is similarly made out of one forging. When finished, each flask is worth about £500,000. Stringent manufacturing and performance standards have to be met. These are drawn up by the International Atomic Energy Agency, which also recommends rules and regulations covering the transport of the flasks. To meet these standards, the industry has developed a comprehensive testing program. Literally hundreds of impact tests have been carried out using scale models, dropping them so that they land from all sorts of different angles. The engineering data obtained in this way can be extrapolated to full size. The tests have met the safety standards laid down by the IAEA and have matched the theoretical performances predicted by computers. But in 1983, to enhance public confidence in the flasks, a program of full-scale testing of an actual production flask under real-life conditions was begun. The complete test program cost £4 million and spanned 4 years. On March the 6th, 1984, Phase 1 of the program was carried out. An actual flask, straight off the production line, was filled with water and loaded with steel bars to simulate fuel elements. It was hoisted over 9 meters into the air and then dropped. The flask was dropped on one edge of the lid to impose the severest possible test of its integrity. In dynamic terms, as far as forces on the flask are concerned, the event was all over in about 20,000ths of a second. In that split second, the projecting parts of the lid were knocked back and the lid moved momentarily away from the body. Some of the bolts stretched slightly. It all happened so quickly that the flexible seals between lid and body could not readjust fast enough, and as a result, a tiny amount of water escaped in the form of an atomized spray. The quantity of water which escaped would, in real life, have had no radiological significance at all and posed no health hazard. But dropping the flask wasn't enough, in the opinion of some MPs and local authorities consulted. Only a full-scale rail crash would really prove the point. So, in July 1984, Operation Smash Hit was arranged. The same flask used in the drop test was fitted with a new lid, filled with a ton of water, and 200 steel bars, once again to simulate uranium fuel rods, festooned with measuring instruments, and mounted on a flat roll, the kind of wagon used for transporting operational flasks. This was then derailed and turned on its side on a stretch of test track at Old Dalby in Leicestershire, as if it were a real accident. The Type 46 diesel locomotive, number 46009, and 3 standard coaches were used to represent a typical passenger train. Dynamically speaking, more coaches would have made no difference to the force of the impact. On Tuesday, July the 17th, these were positioned 8 3/4 miles back from Old Dalby, near a village called Edwalton. The train was set in motion without a driver. Every inch of the journey was followed by cameras mounted on a helicopter, and the train's speed was checked by engineers using radar guns. Eventually, it reached 100 miles an hour. And watched from a safe distance by some 1,500 invited guests, it ploughed headlong into the derailed Flask and wagon. "32 different cameras captured the scene from many different angles. There was even a camera on the front of the engine. But, whichever way you looked at it, it was a tremendous test of the strength of the fuel flask. The draw hook on the front of the locomotive hit the edge of the flask, but the lid stayed bolted in position. There was some scarring of the steel and buckling of the outside cooling fins. But the flask had been pressurized to 6.9 bar before the test, and measurements taken afterwards showed that only 0.02 bar of pressure had been lost, proof that it had remained intact and totally safe for the public had it contained actual radioactive materials. It couldn't have been a tougher test. But it should be stressed that in more than 30 years of carrying nuclear fuel flasks from power stations to Sellafield, covering over 6 million miles and involving more than 14,000 separate journeys, not one single accident has occurred involving the release of radiation or radioactive materials. But then, that's what these flasks are designed to ensure.